In today's session, we will focus on Sequence Models Part 3, where we will explore the use of convolutional neural networks (CNNs) for text classification. We will discuss how CNNs, originally developed for image processing, can be adapted for NLP tasks to identify key features in text data. We'll begin by understanding the basic principle of CNNs and how they extract local patterns such as n-grams in order to classify text. Then we will demonstrate these concepts in Python by building a CNN-based text classification model. In our previous session, we introduced LSTMs and their ability to capture sequential dependencies for tasks like sentiment analysis. Convolutional neural networks offer a different approach, focusing on identifying local patterns, and are often faster and simpler to train. By the end of today's session, you would understand how convolutional neural networks process text data and learn how to implement a convolutional neural network-based text classifier using Python. Let's get started.
Hello everyone, welcome to today's session where we'll focus on Sequence Models Part 3, where we'll look at convolutional neural networks for text classification. This is the outline of what we will learn in this video: basics of convolutional neural networks, from the convolutional layers to poly layers and the fully connected layers, and especially how they apply on text classification tasks. We'll also walk through a hands-on Python implementation of building, training, and evaluating a convolutional neural network-based text classification model using a real-world data. By the end of this session, you would be able to understand how CNNs can be adapted for text classification tasks, pre-process text data for input into a convolutional neural network-based model. You should also be able to build, train, and evaluate a CNN-based model for text classification using Python. You should also be able to interpret performance metrics like accuracy, precision, recall, and F1 score for model evaluation. To begin with, convolutional neural networks are a powerful tool for text classification due to their unique ability to extract local patterns from text data. And they basically use specialized modules like convolutional filters to identify patterns such as n-grams, which are basically sequence of words like maybe not good, very happy, etc., which are very critical for understanding the meaning and context in text. Compared to recurrent neural networks, RNNs, convolutional neural networks are computationally efficient because they process the input in parallel as opposed to being processed sequentially. And this efficiency not only reduces the training time, but also makes convolutional neural networks to be more scalable for larger datasets. Additionally, convolutional neural networks are particularly well suited for tasks that have fixed length inputs, such as sentiment analysis or document classification, etc. This is because they excel at identifying significant patterns regardless of their position in the input. This combination of pattern recognition, efficiency, as well as the robustness of CNN makes it an ideal choice for text classification tasks in natural language processing. Now, before we move forward, let's consider this important question. How can convolutional filters, which were ab initio designed to find spatial patterns in images, work for identifying patterns in sequences of words in text? This is a very fundamental concept when applying CNNs to text classification tasks. In the next few slides, we will explore how convolutional filters adapt to text data, focusing on how they identify local patterns such as n-grams within a sequence. To apply CNNs to text data, the input needs to be converted into a numerical representation that the model can process. And this is basically done by transforming the text into a word embedding matrix, where each word in the sequence is represented as a dense vector. And you can use embedding techniques like word2vec or glove in order to generate these vectors. And if you do that, they will capture the semantic meaning as well as the relationships between words. Okay. Basically, this matrix serves as the input for the convolutional layers, which are then used to identify local patterns like n-grams within the sequence. And this enables the convolutional neural network to be able to understand and classify the text effectively. So neural networks are inherently designed to process numerical data, not raw text. Therefore, before feeding text data such as a review into a neural network, we must first of all convert each and every word into a numerical representation. We must be able to convert each and every word here into a numerical representation. And this process is what we call the word encoding, basically trying to transform words into numerical values that the model can be able to interpret. These encodings ensure that the network can be able to learn patterns as well as relationships between words based on their numerical representation. Now, there are several common approaches, one of which is called the frequency-based tokenization. How does this work? We first of all build a vocabulary by recording all the unique words in the dataset. So each word is assigned a unique integer, or what we call a token, based on its frequency in the dataset. For example, words like the is assigned 0, followed by the next most common word, let's say of, which is assigned 1, and then the next most common word, let's say so, is assigned 2. So this word token mapping is stored in a dictionary-like format, as you can see here. And then once the vocabulary is created, the text corpus is tokenized by converting each word in a document into its corresponding token. And this results in a sequence of integers that the model can be able to process. So for example, if you have a sentence like the pettiness of the whole situation, and then as opposed to feeding this sample text into the machine learning algorithm or neural network, you simply feed the corresponding numerical representation. Of course, for example, if the word the represents 0, the word pettiness represents some value, let's say 121,241, and then maybe of represents 1. It is this particular tokenized text that you feed into the neural network. There is also what we call one-hot vectors, which basically represent each word as a binary vector with a single value of 1 indicating the word's position in the vocabulary, and then all the rest are zeros. We also have word2vec. We've seen that in our previous classes on word embeddings, where we said word encoding with word2vec represents each word as a dense vector in a multidimensional space. So it could be, let's say, 300 dimensions. So every word would have this dimension, isn't it? And basically what we do here is similar words have closer values. So for example, the word the can have, let's say, 0.2, 0.4, minus 0.1, blah, 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 depending on the number of columns that you are using to represent that particular dimensional space. Okay. Let's now understand how convolutional layers work in text. Basically, they use what we call sliding kernels, similar to image processing, but in this case adapted for word embeddings. So instead of square for images, what they use is a rectangular shape to cover for multiple word embeddings at once. just like n-grams. And so the kernel slides over the embedding matrix, multiplying its weight with the embedding underneath, and then summing the values to produce an output feature. And then this allows the convolutional neural network to be able to detect local patterns such as n-grams across sequence of word embeddings. Now let's look at an example of what a pair of filtered word embeddings would look like. So in the slide we have a toy example that shows each word encoded as an embedding with 3 values. The, good, movie, each has 3 values. However, this will usually contain many more values, but just for ease of visualization, we say let's restrict it to 2. So to look at 2 words in this example sequence, since we said we are using 2 grams, isn't it? We can use a 2x3 convolutional kernel. We are using 2x3 because every word has 3 columns, and then we are taking 2 grams, isn't it? So since every row represents 1 word, so if we are taking 2 grams, so it means we are going to take 2x3. If we are taking 3 grams, it will be 3x3, etc. So to look at 2 words, we can use 2x3 convolutional kernels, and then the kernel weights are placed on top of 2 word embeddings. In this case, the downward direction represents time, so the word movie comes right after the word good in this short sequence. So the kernel weights and the embedding values are multiplied in pairs and then summed together to get a single output. For example, here we multiply 0.5. If you're looking at the 2 grams good movie, we have 0.5 multiplied by 0.7 plus 0.4 multiplied by minus 0.5 plus 0.7 multiplied by 0.3 plus 0.2 multiplied by 0.1 plus minus 0.1 multiplied by 0.2 plus 0.3 multiplied by 0.6 in order to get our final answer of 0.54. Now there is also another nice property of this convolutional operation. Recall that similar words will have similar embeddings, and a convolution operation is just a linear operation on these vectors. So when a convolutional kernel is applied to different sets of similar words, it will produce a similar output value. In the example here, you can see clearly that the convolutional output value for the input 2 gram, that's good movie, as well as the fantastic song, are above the same value because the word embeddings for this pair of words are also very similar. So you can see the good movie has 0.54 and fantastic song has 0.53. So what does this tell you? It tells you that the convolutional kernel has learned to capture a more general feature, not just a good movie or a song, but a positive thing generally. Okay? The good movie is something positive, and the fantastic song is also a positive thing. And you can see that the value they have is also closed. So it's just telling you that the convolutional kernel has learned a more general feature, maybe a positive thing. So recognizing this kind of high-level feature can be especially useful in text classification tasks. This is because they often rely on general grouping. For example, in sentiment analysis, a model will benefit from being able to represent negative, neutral, and positive word groupings based on the nature of the review. And a model could use those general features to be able to classify entire text. Now, you've seen how a convolutional kernel can be applied to a few word embeddings. In order to process an entire sequence of words, these kernels will slide down a list of word embeddings in a sequence. This is called a 1D convolution because the kernel is moving in only one dimension, which is time. A single kernel will move one by one down a list of input embeddings, looking at the first word embeddings, and then the next, and then the next, and so on. the resultant output will be a feature vector that contains about as many values as there were in the embeddings. So the input sequence size does not matter. Okay? Here you can see what the output of a 1D convolutional might look like when you apply it to a short sequence of word embeddings. So we have this movie has amazing diverse characters, and you can see how the features are obtained for each and every convolutional operation. Just like in any typical convolutional neural network, one convolutional kernel is usually not enough to detect all the different kinds of features that will be useful for a classification task. So to set up a network so that it is capable of learning a variety of different relationships between words, you would most likely need many filters of different heights. As you can see in this example from this paper, where they used convolutional neural network for text classification, you can see that they use several filters here. One way to identify important features, no matter their location in a sequence, is to discard less relevant locational information. To do this, we can use a pooling operation. There are several types. The most common one is the max pooling operation. And what it does is that it forces the network to retain only the maximum value in a feature vector. Okay? And apparently this should be the most useful local feature. After applying the max pooling operation, the max values produced by processing each of the convolutional feature vectors will often be concatenated and passed to a final fully connected layer. Okay, so whatever maximum we have obtained from each particular max pooling operation, they are usually concatenated and passed to a final fully connected layer, and this fully connected layer can produce as many class calls as a text classification task requires. Now these are the key components of convolutional neural network for text, from the convolutional layers to the stride, to the padding, to the activation function, the pooling layers, and to the fully connected layers. We mentioned convolutional layers as trying to extract features by applying filters over the embedding matrix. And then the stride basically tries to control the step size of the filter. Padding basically adds borders to retain edge features. And then the activation function tries to introduce some non-linearity to capture complex information. And then the pooling layer tries to condense features by aggregating the key information. And then the fully connected layer integrates the features and produces the final prediction. The results obtained after evaluating the convolutional neural network model is usually summarized into what we call a confusion matrix. The confusion matrix is basically a table that displays the true positives, the true negatives, the false positives, and the false negatives. And then it is very useful for understanding the model errors. From the confusion matrix, we can be able to calculate key performance metrics such as accuracy, precision, recall, and F1 score. The accuracy is the proportion of correctly classified samples, while the precision focuses on the accuracy of positive predictions. The recall measures how well the model identifies all relevant instances, while the F1 score is just a harmonic mean of the precision and recall. The accuracy, precision, recall, and F1 score have these formulae, and you can see clearly that all of the variables are obtained from the confusion matrix. The accuracy is the true positive plus true negative divided by the sum of the true positive, true negative, false negative, while the precision is the true positive divided by the sum of the true positive and the false positives. and then the recall is true positive divided by the sum of true positive and false negative, while the F1 score is just the harmonic mean of the precision and recall. That's twice the product of the precision and recall divided by the sum of the precision and recall. Now, apart from the key performance metrics, we can also use visualization in order to evaluate how well our training or how well our model has done. And we often use what we call the learning curves. The learning curves are widely used diagnostic tools in machine learning, especially for algorithms that learn from a training dataset incrementally. The model can be evaluated on the training dataset as well as a holdout validation data. And this is done after each update during the training process. So the plots of the measured performance can be created to show the learning curves. And then if you review the learning curves, you can be able to get useful insights from them. In most cases, you do for both the accuracy and the loss. So you juxtapose the training and the validation accuracy as well as the training and the validation loss. But in order to assess the performance, in most cases, since the loss is often used as the cost function for training these algorithms, so it can suffice. There are three common dynamics that you are likely to observe in learning curves, and these are underfit, overfit, and good fit. Underfitting refers to a model that cannot learn the training dataset, and it usually occurs when the model is not able to obtain a sufficiently low error value on the training set. An underfit model can be identified from the learning curve of the training loss only, so the loss is enough. And it may show a flat line or a noisy values of relatively high loss, and this indicates that the model was unable to learn the training dataset at all. This example here is a common problem with underfitting when the model does not have a suitable capacity for the complexity of the dataset. An underfit model may also be identified by a training loss that is decreasing and continues to decrease at the end of the plot. This indicates that the model is capable of further learning and possible further improvements can be obtained. Probably the training process was halted prematurely. Now, a plot of learning curve showing underfitting can be identified if the training loss remains flat regardless of the training, and if the training loss continues to decrease until the end of the training. We also have overfitting. Overfitting refers to a model that has learned the training dataset too well, including the statistical noise or the random fluctuations in the training dataset. And this often occurs if the model has more capacity than is required for the problem, and in turn gives too much flexibility. It can also occur if the model is trained for too long. And from the learning curve, we can identify overfitting. If the plot of the training loss continues to decrease with experience, and then the plot of the validation begins decreasing to a point and then begins to increase again. Now, what we want is a good fit. That's the goal of the learning algorithm. And it exists between an overfit and an underfit model. A good fit is identified by a training and a validation loss that decreases to a point of stability with a minimal gap between the two final loss values. The loss of the model will almost always be lower on the training dataset than the validation dataset. And this means that we should expect some gap between the train as well as the validation loss learning curves. And this gap is usually referred to as the generalization gap. Some gap between, in summary, A plot of learning curves shows a good fit if the plot of the training loss decreases to a point of stability and the plot of the validation loss decreases to a point of stability and has a small gap with the training loss. And often, continued training of a good fit will likely lead to an overfit. Now, convolutional neural networks can be applied in NLP for sentiment analysis, spam detection in emails, topic categorization for news articles, amongst many other useful applications. And the practical workflow for any CNN-based text classifier is to begin with the data pre-processing, where you tokenize the text into words, you convert the words into embeddings, and then you part the sequence to ensure uniformity, and then you now build the CNN model, which involves inputting the layers for embedded representations, the convolutional layers with filters to extract the patterns, pulling layers for condensing the information, and then finally the fully connected layers for classification. And then we can train the model. This is where we build the model, and then after that, once the model is built, we can now train the model on the training data and then evaluate the performance on the testing data in terms of useful performance metrics such as accuracy, precision, recall, and effort. Let's now have a hands-on demo of building a convolutional neural network for text classification.
So in this demonstration, we are going to show how to use convolutional neural networks for text classification. And for this particular experiment, we are going to use the IMDb 50 dataset that we used earlier. Here is it. Yeah, this is the review. It's an NLP dataset, and then there are two classes, either positive or negative. So we want to use this particular dataset and then train a CNN-based text classifier to be able to classify any given review as to whether it is positive or negative. So as usual, we start by importing some useful, we install some useful libraries, especially when you work with text. There are some libraries that will assist you in doing your work without any problem. Here, we're installing contraction. It's a library which is used to expand contractions like don't, isn't. In English language, there are contractions like don't, isn't. So in English, so maybe if you want to open it and maybe convert isn't to is not or don't to do not. So this is the library that does that. The text search library is a tool for searching specific patterns in text, and it's used for text cleaning or other pre-processing tasks. This TQDM is also a very popular library. Basically, it's just for convenience. It provides a progress bar for loops in Python, and it makes it easier to track the progress of codes that long for a very long time. And then, of course, we have the NLTK, which is the Natural Language Toolkit. It's a very popular library for working with human language data. And then here we are importing the Ponketi tokenizer model, which is used to split our text into either words or tokens. I think I have already installed this, but even if I run the code, it will tell me that I have already installed that. Okay. And then the next thing is to import the necessary modules. Okay. If for you to develop any model in NLP, you have to work with several modules from pandas, NumPy, TensorFlow.keras, and even within TensorFlow.keras.layers, you have several. Okay, for example, the pandas is used for data manipulation, as we all know. Okay, NumPy is for numerical operations. We have sequential here because we are developing a CNN model, and in CNN we stack layers, one layer after the other. So this sequential it enables us to stack layers of stuff linearly, linear stack of layers, and it's used in building neural network. And then the dense here is used for fully connected layer in neural network because we are going to use it. The flatten, it's also used before you apply to the fully connected layer. You need to flatten your input into a one-dimensional vector, and this typically comes before the fully connected layer. And then we also have the conv1D. If we are working with images, we are going to use conv2D, but since this is textual information, we are going to use a special data for text, that's conv1D, and this imports the 1D convolutional layer that's used for processing the sequential data. And like I said, it's clear it's mostly used for text or time series data. And of course, we import our max pooling, okay, for performing our max pooling operations. We import our embeddings, okay. This is an embedding layer which is used to convert our integers that converts the integer encoded words into dense vector of fixed sizes, isn't it? Remember, in text, we have to convert from text to numbers, isn't it? So this embedded layer is used to convert the integer encoded words into dense vectors of fixed sizes. And then it's also used for text reprocessing. And of course, we have our tokenizer and sequences, label encoders. If you want to plot, we use the matplotlib because we are going to plot our loss and the accuracy curves in order to see the performance of how our model is doing. We've treated that in the slides. And then this is just done to ensure reproducibility. So let me run the code here. So I've run the code. The next thing now is to import the IMDb dataset. Okay, we import it. Like you said, this is the IMDb data. We are importing this data into our Python environment. So we simply run it here, and then we can visualize a few rows. Okay, you can see it here. And then here we are saying, since there are 50,000 entries, we are saying let us use from 0. That's like if we want to use 70% of 50,000 would be like 35,000, isn't it? So from the beginning to 35,000 of the reviews, we are going to use that for our training. And also for the sentiments, from the beginning to the 35,000 sentiment, we are going to use that for our training. And then for the testing, the features are going to be the reviews from the 351 review to the last one. That's going to be our testing. And then from the 351,000 to the last one is going to be used for testing. So this like our input data, and then this is our validation or testing data. We are calling this 351 because indexing in Python starts from 0. So let's run this. Okay. The next is text wrangling and normalization. You know that in pre-processing text data, you need to perform several things. Okay, you need to perform several things. You need to remove stop words, contractions. You need to use regular expression to perform several operations. Basically, the purpose of this code is to perform text wrangling and normalization, and this involves several important steps like removing HTML tags, etc., expanding contractions, converting text to lowercase, removing accents, eliminating special character, etc. So we don't have, I believe we have already treated this in our stemming and lemmatization classes in the previous classes. So we've also seen how to work with regular expression. So the basic thing is that this code is an all-encompassing code that tries to clean the text as much as possible. So let's run the code now. If we run it now, and then the next is now to pre-process the training and testing reviews, and we do that by both the training and the testing reviews should be normalized and clean, and then we feed that to this pre-processed corpus function that we have already declared here. Okay, where is it? The pre-processed corpus here that we have defined. We are now calling this particular training reviews and testing reviews on this particular function. And why are we doing this? Why are we doing this? We are doing this to ensure that both the training and the testing dataset undergo the same pre-processing step. And this can result in a consistent format that's suitable for model training and evaluation. So let's run this. Still running. Still loading. Let's just wait for it to finish. So the next step is to create and configure a tokenizer to process the text data. And this is done by converting the words into integer indices and then preparing the tokenizer for handling out of vocabulary words. And then this is the code that does that. We simply run this, still pre-processing, isn't it? And then the next is to inspect the tokenizer's vocabulary by finding the word with the highest index, the word with the lowest index, okay? And then the index assigned to the UNK out of vocabulary token, and we do that by using this particular lambda function in Python that does that. Okay, so we just run the code here. Okay. Yeah, the next is now to convert the normalized text reviews into sequences of integers using the train tokenizer. And basically, this prepares the data for input into our machine learning or what we call the deep learning algorithm, because convolutional neural network is a deep learning algorithm. So let's do that for the training sequences and also do that for the test sequences. Let's wait for it still. Okay, let's do that for the test sequences. Okay, and then at this point we can print the vocabulary size and the number of documents. Okay, and then at this point we can even visualize this particular plots for both the train sequences and the test sequences. So let's run this. Basically, this plot, this code here, the purpose of this code is just to visualize the distribution of the number of words of the tokenized sequences for both the training sequence and the testing sequence. And why are we doing this? This will help us to understand the variability in the review lengths. Okay? What's the length of the reviews? And this will aid us in deciding the appropriate sequence length for padding or truncating. So you don't just want to blindly truncate or pad. So you have to look at the frequency of the words and then the number of text. And then from here you can see that maybe picking the length to be 1000 should not be a bad choice, because we are going to only pad a few instances. So in this case, we make our maximum length to be 1000, informed by this plot. Okay, we make it to be 1000. Okay, and then at this point we pad the dataset to a maximum review length in words. This for the training X train, and then this for the X test, isn't it? So let's run this. Okay, as you can see that now each and every review has a maximum length of what? Of 1000. For the training data, we have 35,000 by 1000, and for the testing data, we have 15,000 by 1000. So even if a sentence is more than 1000, which from this plot, there are only a few of them. What we need to do is just to truncate, isn't it? Just to truncate. And those that are less than 1,000, we just pad those, isn't it? Yeah. So in this case, we can now here, since our reviews here, from here, it's either negative or positive, negative, positive, and we do not want to work with this. So what we can do basically is to encode, and then that's why we're calling this label encoder from pre-processing. And then the number of classes are 2. It's either positive or negative. And then if you do this encoding, it would encode the positive class to 1 and the negative class to 0. So, and then here we now fit the transforms for the train sentiments, and then this will be for the Y training, and then this will be for the Y testing. This one will be that 5,000 vector of ones and zeros, and this will be 15,000 vectors of ones and zeros, isn't it? So let's run this, and then here we can set the vocabulary size. Okay, and at this point we can now begin to prepare our model for training. Our embed size to be 300, epoch 5, batch size to be 128. This embed size 300, this specifies the dimensionality of the word embedding. Okay, and then the epochs here defines the number of complete passes through the dataset during training. So we want to do 5 epochs. You can raise it to higher value, but because we are just demonstrating, so we leave it to 5. And then the batch size, of course, controls how many samples are processed before the model updates its weight. So we are setting this to 128. And then this is where we created our model. As you can see, it's a sequential model. So like I told you earlier, here we are setting the model to be a sequential model, which means that the layers are added one after the other in a linear stack, isn't it? And then the next one is to add this embedding layer. Okay, so what is this? This layer, this embedding layer, is the one that's responsible for converting the integer sequences into dense vectors of fixed sizes. Of course, we've set our vocab size, our embed size to be 300. Okay, we have our input length to be maximum sequence length, etc. And then here, this our first convolutional layer is a 1D convolution. Okay, we're specifying the number of we're saying the filter size, the filters to be 128, the kernel size to be 4, and then we are setting our padding to be same, and then we are using activation function, isn't it? So we are using 128 filter. In the class I told you that it's practical for you to use several filters. So in this case, we are using 128 filters for the first convolutional layer, and then we are now condensing using this max pooling layer before we now have another convolutional operation. Of course, the ReLU activation function is just to introduce non-linearity to the function. Okay, so we have our second convolutional layer with the max pool layer, our third convolutional layer, but this one has 64. This one has 64 filters. This has 32, and then if we are done, before we feed to the fully connected layer, we have to flatten. If we flatten, and then we have our dense layer. Okay, we have our dense layer, and if you look carefully, you see that the dense layer has 256 units, isn't it? With a rectified linear unit, isn't it? So it's this layer that learns the high-level features from the flattened output, and then before we now feed to the final output layer that does the classification, and that one has a sigmoid activation function. Okay, why are we putting sigmoid? Because we have only 2 classes. If you have more than 2 classes, that's a multi-class classification problem, then you cannot use sigmoid, you have to use softmax. Okay, so if it is if you're using multi-class, here will be softmax. Okay, but since it is binary class, we have to leave it as sigmoid. And then here we are using a binary cross entropy. If we are using a multi-class classification problem, we are not going to use binary cross entropy as our loss function. We are going to use another one called the categorical cross entropy. Of course, we are using Adam optimizer. It's a very popular optimizer which adapts the learning rate during the training, and it's very efficient for training convolutional neural networks. And then in order to evaluate the model's performance during training and testing, we are going to also visualize the accuracy. And then at the end of the day, we can just visualize the summary of the network. So let's run this and see what's happening. Okay, so this is now the architecture of the model. As you can see, this is the first embedding layer, the convolutional layer, max pooling layer, another convolutional layer, etc. Okay, so don't bother about the naming convention _3_2. That's because I've run similar code on the same environment before running this. It doesn't matter, it's just a naming convention. And the total number of parameters are 53 million parameters. Woo, that's huge. And all of them are trainable. It means we've not frozen any. So all of the total parameters are going to be trainable. What we mean by parameters, we mean the number of weights that will be updated and the biases during the backpropagation algorithm that is used for training this particular algorithm. So the next one is to train the model. And in convolutional neural network, you use this model.fit to train the model. Okay? And remember, if you are training, you feed in only the training features and the training levels. Okay? And then all of these other ones are parameters that you can set. Here we set the epochs to be 5. Okay? The validation split. Sometimes as the model is trained, you need to have a separate validation split just to be sure that what you are training is doing the right thing. So 10% is given for the validation split and then 90% for the training to guide the training process. And then our batch size has been set to batch size. I think we said our batch size was set to around 128, I think. Yeah, we set our batch size to be 128 and then the epoch size to be 5. So, and then verbose is 1. If you said verbose is 1, it means when you are training, you are going to see exactly what is happening. Okay, you're going to be seeing the progress. If you said verbose to be 0, you will just be seeing that this is active, but you're not seeing any progress. But because I want to plot the validation curves, so I have set this to history. So the entirety of this is set to history, so that I can now use history to track the validation processes at each particular epoch. And then this is where I'm plotting the training and the validation curves. Remember, during our class, we said in order to evaluate how well your model is doing, it's always very important for you to plot both the accuracy as well as the loss of the validation curves. So this is what we're doing, and we're going to use 5 iterations. So let's run this. Okay. We're still in the first epoch. This can take some time, so maybe, and the video cannot be more than 1 hour. So you will just I will pause it, and then when it finishes the training, then we'll continue from there. So the second epoch has started. It's also progressing. Yeah, still progressing. Almost done with the second epoch. So this is the fourth epoch, and we can see that the model is progressing. In the first epoch, the validation accuracy was 0.9, the validation loss was 0.2. For the second epoch, it has dropped to 0.8 and 0.3 respectively, then 0.89, 0.4, and then in the fourth epoch, let's see what happens. So it has entered the fifth epoch, and okay, so we are almost done with the fifth epoch now. You can see, like I said, I do not want to, if you say we have to allow it to run for every particular step, then the video would be more than the 1 hour. So that's why I usually stop recording and I only show the important steps. So I think it's almost finishing now. Okay, it's almost exiting the fifth, yeah, 238 of 247, 240, 241, 242, 244, 240. Yeah, I think it's done now. Okay, as we can see now, the plot generated two plots. The first one is the training accuracy, and then the second is the accuracy curve, and then the second one is the model loss curve. So why is this important? The accuracy plot displays how the model's training and validation accuracy change over each and every epoch. Okay, we had 5 epochs. So we're seeing the progress from epoch 1 to epoch 2 was happening. And for the loss also, we're seeing how it is progressing. Okay, so this helps us to evaluate how well the model is learning, and a steady increase in training accuracy, okay, and a stable validation accuracy will indicate a good learning. Apparently, there is some problem here because with respect to the accuracy, as the training accuracy is increasing, the validation accuracy is decreasing. It increased for a few times and then it decreased here. So that's because we used only 5 epochs. And if this continues as we increase the epochs, then it's clear sign of overfitting. And we've discussed that adequately in the slide. And also for the loss, you can see that for the training loss, as the epochs increase, it is what? It is increasing. The loss is as we move from one epoch to the other, the loss is decreasing, it's coming towards 0. But unfortunately, the validation accuracy as we increase the epoch is now raising. That means this particular model of ours is overfitting, and as an assignment, you should go and find out what we will do to this model to overcome this particular problem, because it's an inherent problem in deep learning. Okay, but I think we now understand why it is important for us to have certain mechanisms in place to ensure that our model does not overfit. This is just a basic illustration, so we are not showing those particular techniques. Now at this point, it's time for us to evaluate the trained model. And like we said, when evaluating, you feed the testing data, the test features and the test labels, and then we want to see the result as a percentage, so we simply do that. Okay. Okay, we are saying that the accuracy is 87.97%. Well, it's just an illustration, so it's not bad. And there are mechanisms we can put in place to ensure that we get even a better accuracy. Now, this particular code generates the predictions. It generates the predictions on the test data, and it uses this particular method predict, and then thereafter it converts the predicted probabilities into a binary labels. Whenever it is more than 0.5, we assume that it is a positive class, and otherwise it is in the negative class. And then we want to also display the first 10 predictions, just to be sure that so it's running. This is where the binary class predictions that we obtain above, those above 0.5 and those below 0.5 are then converted to classes. So if it is above 0.5, we say it is positive, and if it is below 0.5, we say it is negative. So this is it, 0, 1, 0, 0, 1. So for this, it will be 0, it will be negative. So it will be negative, positive, negative, positive. So let's run the code and see it. So you can see that this was happening. And then at this particular point, we can evaluate the performance of the model using two important metrics. That's the classification report here, as well as the confusion matrix. So the classification report will give us a summary of the classification in terms of accuracy, precision, recall, and then you can also see the confusion matrix that we discussed in the class, talking about the true positive, the true negative, the false positive, and the false negative. So let's run this. So if you run this, this is the classification report, and then this is our confusion matrix. So this is the true negative, this is the negative, actual negative, and then this is the predicted negative. So this is the true negative, and then this is the true positive, and then this is the false negative, and then this is the false positive. And then at this point, we can now try to write a simple code that can be able to pick any external sentiment review, and then we see what the result is going to be. As usual, we are going to have the same type of process, because the process you use in encoding the review during training, you have to also do that if you're evaluating, because your model only understands numerical values. So you have to pass that to the pre-processed single text that you've declared earlier, and then also to predict the sentiment. Okay, and then if you do that, then you can have any raw text here that says the plot was thrilling at all and kept me engaged throughout the movie. So this is this clearly a very positive review, and let's see what our model is going to predict. So it says the sentiment is positive and the probability is 0.99. Let's give another negative review. Let's say the plot was not interesting, was really messy, was really and not interesting. Or not interesting. I regret watching the movie. Let's see what we have here. So we run this. It says this is a very negative comment with a probability of 0.11. So this brings us to the end of the Python illustration, and I believe each and every one of you will now have an appreciation of how a convolutional neural network can be used for text classification.
The key takeaways for today's class is that convolutional neural networks are effective for capturing local patterns in text, and they are also computationally efficient and work well for tasks like sentiment analysis and topic classification. As usual, this is an assignment for you where you are to build a CNN-based text classifier on a real-world data. You are to download and pre-process any text classification dataset from any repository of your choice, And then you are to build a CNN model with the following layers: an embedding layer, a convolutional layer, a pooling layer, a fully connected layer, and then you train the model and evaluate its performance. And then write a brief report summarizing the pre-processing steps, the model architecture, and the results you obtained. These are some useful resources for further reading. In our next class, we shall look at NLP applications. Thank you very much for having me.
Well done on completing today's class. Let's quickly recap the key points we've covered. We discussed how convolutional neural networks (CNNs), originally designed for image processing, can be adapted for text classification tasks. We explored the core components of CNNs, including convolutional layer, pooling layer, and fully connected layers, and how these components are used to extract local patterns in text data. Finally, we implemented a CNN-based text classification model in Python, highlighting the practical steps for building, training, and evaluating the model. A memorable takeaway from today's session is that convolutional neural networks excel at capturing local features in text data, such as n-grams, while being computationally efficient, making them a great choice for tasks like sentiment analysis or spam detection. To ensure you're practicing and reinforcing these concepts, I have prepared an assignment for you. Upload your completed assignment and report to the Learning Portal. The full details will also be available on the portal. Reach out to a teaching assistant or engage via the discussion forum if you encounter any challenges. Thank you for being an active participant in today's session. Keep practicing, and I look forward to seeing you progress in the next class. See you soon.